Have you ever wondered how it's possible to find a needle in a haystack of data? And I don't mean just any needle, but the exact right one, in like milliseconds. Well, that's the magic of what we call similarity search. And today, we're going to demystify Faiss, the powerhouse library from Meta AI that makes it all happen. You know, the secret behind all this is something called similarity search. See, these platforms, they turn everything, songs, products, even your own preferences, into a long list of numbers. It's kind of like a unique digital fingerprint called a vector. So when you listen to a song you love, the system's job is to find other songs with a really similar fingerprint. Faiss is the supercharged engine that just sifts through billions of these fingerprints almost instantly.
So here's our game plan. We're going to climb what I'm calling an optimization ladder. We'll start at the very bottom with the most basic brute force approach. Then, with each step we take up that ladder, we'll unlock a new technique that makes our search smarter, faster, and way more efficient. Okay, so what's the fundamental challenge we're even talking about here? Well, your traditional databases, they're fantastic at finding exact matches. You search for a name, you get that name. But finding similar items, that's a whole different ballgame.
Right, so the technical term for this is a k-nearest neighbor search, or KNN. The best way to think about it is like this. AI plots every single item on this giant, incredibly complex map that has hundreds of dimensions. A vector is really just the set of coordinates for one item on that map. So finding a similar song literally means finding the song that's physically closest to it on this crazy invisible map.
Now, the most obvious solution is to just, compare your song to every other song in the database, one by one. But when you have billions of songs, that's just impossibly slow. This is what people call the curse of dimensionality. As you add more data and more features, the space you have to search just explodes. It doesn't scale at all. We need a shortcut.
And that shortcut is called Approximate Nearest Neighbor Search, or ANN. And honestly, this is where the genius comes in. The core idea is, what if we don't need the perfect answer every single time? What if really, really good is actually good enough? By giving up just a tiny bit of accuracy, like, say, finding 99 of the top 100 matches instead of all 100, we get these enormous, massive gains in speed. This trade-off, speed for good enough accuracy, that is the entire philosophy behind Faiss.
So, let's step onto the very first rung of our ladder. This is our baseline, the simple, perfectly accurate, but totally unscalable method.
In the world of Faiss, this baseline is called index flat L2. And it does exactly what we talked about, that exhaustive one-by-one comparison. It calculates the straight line distance, what mathematicians call the Euclidean or L2 distance, between your query and every single other point on the map. You get 100% perfect accuracy, but as we're about to see, that perfection comes at a very steep price. This is our gold standard for accuracy.
And here's the scorecard we're going to use to track these trade-offs. As you can see, Index Flat L2 gets us perfect, 100% accuracy. But the cost? It's incredibly slow, and it uses the full amount of memory. This is the benchmark we need to beat. All right, time to climb to the next rung. Instead of working harder, we're going to start working smarter. Why would you search an entire library if you already know which section the book is in?
This is done with something called an inverted file index, or IVF. The big idea here is to pre-cluster all the data into little neighborhoods. The technical term is Voronoi cells. It's exactly like setting up sections in a library. When a new search comes in, you don't look through the whole building. You first figure out which sections are the most promising and only search there.
So it's basically a three-step process. First, during a training phase, Faiss uses a clustering algorithm to find the center points for all these neighborhoods. Then, when your query comes in, it quickly finds the closest neighborhoods, not the individual items. And you've got this little knob, the nprobe to parameter, that lets you decide how many neighborhoods to check. Finally, it does a quick, exhaustive search, but only inside those few areas you picked, ignoring literally everything else.
Let's get back to the scorecard. With index IVF flat, look at that change. Our speed is now fast, which is a huge improvement. The price we pay, of course, is that our accuracy is now approximate. But notice the memory usage. It's still full. We haven't actually compressed anything yet. So we've solved for speed, but our index is still massive.
And that brings us to the third rung of our ladder, which is all about tackling that memory problem. For data sets with billions of items, just keeping every vector in RAM is a huge challenge.
This solution is this really clever technique called product quantization, or PQ. And you can basically think of it like a zip file, but for vectors. It takes a long, very precise vector and chops it up into smaller pieces. Then, for each little piece, it finds the closest match from a pre-built codebook of possibilities and just stores the short little ID for that match. It's a way to dramatically shrink the vector size.
And the results of this? They are absolutely staggering. We're talking about a memory reduction of over 97%. A vector that used to take up 512 bytes of space can now be shrunk down to just 16. This is the breakthrough that allows us to actually fit an index of 1 billion items into a computer's RAM. It's a game changer.
And now, our final scorecard tells the whole story. By combining the partitioning from IVF with the compression from PQ, we get the winning formula: Index IVF PQ. It's the fastest option we've seen, the memory is highly compressed, and the accuracy is still really strong. We've built an index that hits that perfect sweet spot: fast, light, and totally effective for real-world use cases.
Okay, we've now reached the top of our optimization ladder, and this is where Faiss really shines. It allows you to combine all these building blocks to create your own hyper-optimized custom solutions.
You see, Faiss treats all these different methods, the partitioning, the compression, even pre-processing steps, like they're Lego blocks. You can stack them together however you want to build what's called a composite index. It's a multi-stage pipeline that's perfectly tailored to your specific data and your performance needs. So a real-world, high-performance recipe might look something like this. You start with a pre-processing step to get the data ready. Then you use IVF to partition it all up. Inside those partitions, you store the data using those compressed PQ codes. And then for the final touch, you can add a refinement step, where you take, say, the top 100 approximate results and quickly re-rank just those with their original full-size vectors to get the absolute best of that batch. It's a whole pipeline built for peak performance.
And the toolbox has even more to offer. For the ultimate performance, there are graph-based methods like HNSW. Instead of clusters, it builds this multi-layered network between all your data points, kind of like a 6 degrees of separation thing. It is incredibly fast and almost perfectly accurate. So what's the catch? Well, it's memory hungry. So it's the perfect choice when speed and accuracy are everything and you've got the RAM to spare.
But even with all these other fancy tools, the original Faiss researchers themselves said it best. The IVF-PQ combo is still probably the most useful indexing structure for large-scale search. It's just the powerful, reliable workhorse of the Similarity search world.
And that brings us to our final thought. We've climbed this ladder all the way from a simple brute force search up to a sophisticated, compressed, and partitioned index. But as we know, the world of data is always expanding. As we move from billions to trillions of vectors, the fundamental challenge stays the same. How do we keep balancing speed, accuracy, and memory? What new techniques are going to form the next rung on this ladder? That's really the question that's driving the entire future of search.